Hello and welcome to this webinar titled Electromagnetic Simulation Inside Autodesk Inventor. My name is Arvind Krishnan and I will be your host today. Let us look at the agenda for the day. I'm going to start with talking about EMWorks products, about the company, and also the applications where you can use our product. Then I'm going to spend a lot of time in this webinar showing you a live demonstration of our product inside Autodesk Inventor. I'm going to use a couple of models to do the same. And finally, I'm going to open the floor for question and answers, where you will ask me any questions pertinent to this presentation or in general to the applications that EMS for Inventor will cover. You can use the chat window that is there in the GoToMeeting. So when you go to the chat, you are welcome to type in your questions, and towards the end of this presentation, I will be happy to answer them. Okay. Also, another bookkeeping item. I'm going to record this webinar and you will shortly receive an email with a link to this recording. In case you want to go back and look at this webinar with respect to anything in particular, that facility will be available to you. And thank you again for joining us today, and good afternoon. And my name is Arvind and we are going to start this webinar now. So let me start by giving you a brief outline of our company. Our company, who's called Electromagnetic Works, is really a pioneer in CAD embedded simulation softwares. Our software that is embedded inside Autodesk Inventor is called EMS for Inventor, and it is used for electro-thermo applications. Now, let us look at the brief products and bundles that we have inside Autodesk Inventor. We have two different bundles inside Autodesk Inventor. We start with EMS Professional. Now, EMS Professional comes with 6 different solver types. We have the electric modules, which cover the electrostatic, electric conduction, and AC electric. And we also have the magnetic solvers in the form of magnetostatic, AC magnetic, and transient magnetic. Now, any of these solvers can be coupled with our thermal solver, and that's just an add-in product that you can select. Now, we have both activation as well as network-based licenses for these products. Then activation is the default license type, and for an additional cost, we can provide you with a network license. The next bundle that we have is the EMS Premium Bundle. The EMS Premium Bundle certainly covers all aspects of EMS Professional, like all the 6 solvers are included. In addition to it, the coupling to thermal as well as a feature called parameterization is included in the EMS Premium Bundle. Now, EMS for Inventor is a low frequency electromagnetic simulation product. It covers from DC voltage or DC currents all the way up to several hundred megahertz of AC excitation. As you can see, there are several different application areas that fall under this spectrum. So we're going to start with electromechanical, which is by far the most used application for this product. So in the realm of electromechanical simulation, you can do linear actuators, rotary actuators, relays, magnetic levitation, voice coil, loudspeakers, solenoids, etc. In the realm of electromagnetic simulations, we have you can simulate permanent magnets, you can simulate non-destructive testing coils, high power applications, transformers, etc. In the area of power electronics, bus bars, transformers, inductors, simulation of these devices are possible. And we range across several industries: aerospace, automotive, consumer goods, energy, power sector, and life sciences also. Now, with this, I'm actually going to show you the product and then we will see two demonstrations today. The one on your left is a magnetic circuit. We're going to compute the force acting on the blue part. And the one on the right is a solenoid, and we would like to understand what is the force acting on the plunger at various positions of the plunger. So without further ado, I'm going to share Autodesk Inventor, and we're going to take a look at how we can do a simulation inside Autodesk Inventor. Okay, as you see here, this is a model of a magnetic circuit. And here we have a coil that is shown in green here. And then we have a steel material. And then we also have another steel which is shown in blue. And then there is some air gap between the two steels. And the objective of this particular simulation is to find out the force acting on the blue component when you apply a particular excitation on the coil. Now, to do a simulation inside Autodesk Inventor, you have to create the model in Inventor, and that's pretty straightforward. And I guess most of you are proficient in creating models in Autodesk Inventor, so that will not be the topic that we will discuss today. Nevertheless, once you create your model inside Autodesk Inventor, you can go straight away to the Inventor Feature Manager, the EMS Feature Manager. If once you install EMS for Inventor, this will be automatically enabled. And the first step in creating a simulation inside Autodesk Inventor is to create what is called as a study. Now, when you create a study, there are several different study types that are available. If you refer back to the slides, I told you that the EMS Professional has 6 different solver types, and that's what you see here. So we support magnetostatic, AC magnetic, and transient magnetic. These are the magnetic solvers. And we also support electrostatic, electric conduction, and AC electric, which form the bulk of our electric solvers. For this particular demonstration, we are going to use the magnetostatic solver. When you say OK, EMS automatically creates a study tree, as you see here. Now we can proceed with defining more components in the form of materials, coils, etc. Now the next step is to actually define materials to the various components. So we have an air box here. Obviously, the electromagnetic field is not just in the solid materials, it's also going to be in the air region around the model. So one needs to model an air box inside Autodesk Inventor. We've done that, and we need to assign a particular material for the same. So to assign a material, we just right click and say apply materials. EMS for Inventor comes with its own material library where you can choose the materials and you can apply to the various components. Now the two air gap here that we have are also going to be applied the material air. The coil that we have is obviously made of some conductor material, say like copper. We apply. And then the two pieces of steel are then applied, say steel 1010. So I open the place where we have steel. So you can look at the permeability, the BH curve, and so on, and one can apply steel. Now, I want to bring to your notice that EMS has a fully customizable material library wherein you can use these predefined materials, or you can even create your own materials and use that for simulation. So once you define all the materials, we have now closed the material library, and we are now ready to define further. The next thing that I'm going to define is to define what is called as a coil. So I'm going to right click and select a wound coil. Now this is a half symmetry model, so I'm going to just exploit that symmetry and use half, and I select the coil component. And I also now go ahead and select the phase through which the current enters and the phase through which the current leaves. So I can show a preview that shows you arrows, how the current enters the coil and current leaves the coil. I can specify a number of turns, say we have 300 turns, and then we have a current of 1 amp. Once your coil is defined, you can just validate, and that defines the coil. So you can actually take a look at the coil defined. It's right under the study tree under coils. Once you have defined the coil, we need to now define the force acting on the blue part, the steel part. So to define a force, you can just pick from the screen the component where you want the program to calculate the force. And finally, because we are doing a symmetric problem, we want to apply a symmetry boundary condition in the form of tangential flux. So I'm going to select all the symmetry phases, and I'm going to apply a tangential flux boundary condition. By doing a symmetry application, we reduce the size of the problem, thereby reducing the time taken to solve the problem without compromising on the results. Once we have defined all of these, now we are ready to run the simulation to take a look at the results. To run the simulation, we just right click on the study and select run. Once the simulation is complete, we will be able to take a look at the results. Now it's running. EMS makes use of the multi-core in your machine. As a result, large problems can be solved using multiple cores of your machine in hardly any time. As you see here, within less than a minute, EMS is able to compute the results. Now we can take a look at the results. The first thing we are interested in is to compute the force acting on the blue component. To be able to compute the force, we just look it up in the result table. So when I double click on the result table, you can take a look at the force. The force is in the, it's an attractive force, obviously, which attracts the blue component towards the yellow component. And that force is about 1.19 or 1.2 newtons. Now we can take a look at the magnetic flux density in the model. So let's go ahead and make a plot of the magnetic flux density. Now you can see here the plot of the magnetic flux density. You can see the maximum value, which is close to about 0.8 Tesla for the current that we applied. And you can see most of this high flux occurs right around the coil. And you can see the flux distribution throughout the magnetic circuit. One can also do a vector plot. So we can create a vector plot of the magnetic flux density. This helps us to visualize the flux lines as vectors. You can see the vector plot of the magnetic flux density. And one can actually go ahead and take a look at modify the vectors and so on. So you can see now the flux lines, the distribution of flux lines inside the circuit in the form of a vector plot. Okay. And last but not the least, we can also create 2D plots. What happens if you want to understand how the flux varies along a particular straight line? To be able to do that, you can create what is called as a 2D plot. And you can select, say, a couple of points that I created in Autodesk Inventor. And you can take a look at how the flux varies from, say, 0.4, work point 4 to work point 5. Now this is the 2D plot that plots the variation of flux between any 2 points in the model. If you want to look at those values, they are listed here, and you can export them either as a text file or as a CSV file and take it to the other programs of choice. So next, let us take a look at another problem that was solved using Autodesk Inventor and EMS for Inventor. Now this is an example of a solenoid. You see a cross-section view of a linear actuator. The blue part is a plunger that moves inside the solenoid. There is also a steel casing that encloses the coil that you see here. Okay, so the three main components of this solenoid are the steel casing, the plunger, and the coil. Now shown as a section view, this is kind of very easy to understand what's going on here. Now in this particular example, we have various positions of the plunger. Okay, and we would like to understand what is the force acting on the plunger at various positions. As before, when we go to the EMS feature manager, we have several studies that relate to the position. For example, let's just open the study where the distance between the end and the plunger is about 19 millimeters, and let us take a look at some of the results. So as before, you can take a look at the magnetic flux density as a section plot here. You can see the flux density distribution in the solenoid. You can also take a look at the results in the form of the force acting. So here I have the force acting on my solenoid, the major force in the y-axis, that's about 11 millinewtons. Okay, and now how does this force vary at various distances? For example, if this was 19 millimeters, and let's take another particular distance and take a look at the magnetic flux density. This is at a distance of 8 millimeters. You can see that the solenoid is more closed. It just comes before, and you can see what is the force acting in this case. That's about 150 millinewtons. Compare that to 11 millinewtons we got earlier, and you can see how the force varies. Now, to be able to compare the force on the plunger for various studies, I can compare the study results across multiple simulations. And I can select the force acting in the y-axis, and then I can even plot them across my various simulations. As you see here, these are the force values. Of course, the minus value tells you that it is in the minus y direction, trying to close the solenoid. And you can see the maximum force when the gap is 8 mm, and the force is much lower when the gap increases. Okay, so one can resort to multiple simulations inside EMS for Inventor, where you can study how the force or any quantity varies as you vary the geometry or as you vary the distances and so on. So with these two examples gives you a very good idea of EMS for Inventor, the workflow, what types of problems you can solve, and so on. And just as a recap, we saw today EMS for Inventor. It is an add-in product from EMWorks that is completely embedded inside Autodesk Inventor. It can do electromechanical, and thermal simulations right inside EMS for Inventor. We also saw two demonstrations. One is a magnetic circuit to compute the force and the magnetic flux, and the second one is a typical solenoid where we have computed the force acting on the plunger at various positions. Now, I want to thank you all for attending this short demonstration webinar, and I want you to be aware that you can visit our website emworks.com if you want to get more information about EMS for Inventor. You can also visit our white paper section and customer testimonials, and also we have an entire YouTube channel that is dedicated for EMWorks products, where you can see multiple videos showing you various capabilities of the product. Now, with this, I'm going to take a look at some of the questions if you may have. So if there are any questions, I encourage you to type it into the chat window. If not, I thank you all for attending today's webinar, and we will send you a recording to this webinar shortly via email, and hope you guys have a great day. Thank you very much, and see you in a future webinar. Bye-bye.